Welcome to our General Chemistry 2 class. In this video, we're going to continue our discussion on thermodynamics. The objectives will be: number 1, predict the spontaneity of a process based on entropy; 2, explain the second law of thermodynamics and its significance; and 3, use Gibbs free energy to determine the direction of a reaction. Let's first have the definition again of thermodynamics. In the last video, we defined the science as the study of the interconversion of heat and other forms of energy. We also had the first law of thermodynamics, which states that energy is neither created nor destroyed but may be transformed from one form to another. This first law is based on the law of conservation of energy. It asserts that energy in the universe is constant, that it is neither created nor destroyed but just transforms from one form to another. So, for example, from solar energy may be transformed to heat energy, and then heat energy may be transformed to mechanical energy, to electrical energy. All this energy are just interchanging in terms of forms. All the energy lost by systems are just being transferred out or expelled to the surroundings. So energy is constant. It is conserved. But what is the importance of studying about thermodynamics? As far as the chemists are concerned, it is useful in determining whether substances that are brought together will form the desired products. For example, in industries or in laboratories or in manufacturing companies, they are after whether reactants will form the desired products. So that's basically the importance of the study of thermodynamics. Before we go to our um, next lesson or the continuation of our lesson on thermodynamics, I need you to identify from the following processes those that are natural. Number 1, you think it is natural. Let's see. Waterfall running downhill is a natural process. Water from below the ground will not go up naturally. So this is a natural process. Another is a lump of sugar dissolving in a cup of hot water. But if you expect the sugar to form again from being dissolved, that will not happen naturally, because naturally sugar dissolves in hot water, but the opposite process is not natural or is not possible. Number 3, iron exposed to water and oxygen forming rust is also a natural process. When a piece of iron is exposed in air which has water, oxygen, because of chemical reaction between iron and oxygen and water, for rust forms. So this is a natural process. Number 4, heat flows from a colder object to a hotter object. Yes, you should know that it is not a natural process, because naturally heat is transferred from hotter to colder, not the other way around. So this is not a natural process, but the opposite is, which is flow of heat from hotter to colder. And number 5, ice melting at 0 degrees Celsius. When you when you take out piece of ice from your freezer, it will start to absorb energy from the surroundings. So if it's negative, it's in a negative degree Celsius temperature, it will continue to absorb heat energy until its temperature becomes 0. And then at 0 degrees Celsius, it will start to melt. And this happens naturally. So this is another natural process. So what is common among these natural processes that we identified from this list of processes? They are occurring naturally at a certain set of conditions. And these processes that occur spontaneously in one direction under a set of conditions, but cannot take place spontaneously in the opposite direction, are called spontaneous process. So like sugar dissolving in water, this is a natural process. It occurs naturally in in one direction but not in the opposite direction. Iron forming rust over time with oxygen in and water. The formation of stalactites and stalagmites because of the chemical reactions that occur in caves. We also have here the expansion of gas particles from one bulb to another. This is also a natural process. We also mentioned in the first law of thermodynamics that a system may lose or absorb energy from the surrounding or into the surrounding. So if a system, for example, loses energy, that energy lost by the system will go to the surrounding. On the other hand, the system may absorb energy from the surrounding. So energy is being transferred from the surrounding to the system. And for that energy that is lost or absorbed by a system can be denoted by the thermodynamic function called enthalpy, denoted by capital H. This is the measure of the amount of energy heat given off or absorbed by a system during a constant pressure process. So if a system absorbs energy, you expect a positive enthalpy. There is an increase in the heat energy. On the other hand, if it's negative enthalpy, we expect that the system gives off energy. So there is decrease in the enthalpy in the system and therefore a negative value of enthalpy or enthalpy that is less than 0 for exothermic, loss of heat energy, endothermic for the gain of heat energy. So if we have enthalpy in the first law of thermodynamics, we have entropy. Entropy is another thermodynamic quantity described as the measure of how spread out or dispersed the energy of a system is among the different possible ways that system can contain energy. So in simple terms, entropy is the measure of the disorder in a system. So the higher the degree of disorder, the higher the entropy. So it's like in common terms, mas dispersed yung particles or yung objects, mas mataas ang measure ng entropy. Mas organized, mas mababa ang entropy. So entropy is the measure of the degree of disorder or the measure of how spread or dispersed are the particles in a system. So in this case, we are talking about the energy, how the energy in a system are dispersed or spread out in different possible ways that this system can contain energy. What are these possible systems? We all know that particles, even in solid, are in constant movement. Take note that particles exhibit different motion, different types of motion. They can exhibit translational motion, rotational motion, vibrational motion. So the greater the possible ways to contain the energy, the higher the possibility for the dispersion of energy. So if we have two possible ways of dispersing energy in a system, comparing that to three or more possible ways of dispersing the energy in the system, then you expect the entropy in the system of higher possible ways of dispersing the energy to have greater amount of entropy. The occurrence of a particular dispersion or distribution is what we refer to as the state of the system. And it depends on the number of possible ways that we refer to as the microstates in which the distribution can be achieved. So the dispersion, the disorder is the state, and the possible ways of distributing the energy, for example, is what we consider the microstate. So the greater the number of microstates, the greater the degree of dispersion or the state. If we have changes in enthalpy, in the first law of thermodynamics, we also have changes in entropy in this lesson. So let's compare the entropy between a solid and a liquid. But considering the transformation of the solid to its liquid state. So notice if it's the same substance, solid turning liquid is increasing the disorder of the particles. So in solid, particles are in compact arrangement. The particles are in more orderly um, arrangement. In liquid, there is a greater degree of disorder in terms of the particles. So that alone can tell us that the entropy in liquid is greater than the entropy in solid of this particular substance. So if we are to compare the entropy between the liquid and the solid, it is greater in liquid than in solid. So the greater the spaces for the particles to move around, the greater the dispersion, the greater the chances for them to be dispersed or spread out in the system. So the greater also the microstates, the spaces are giving them um, higher chances for their movements, for their vibrational movement, rotational movement, translational movement. Okay, kinetic energy is also increased as solid turns to liquid. Another is the transformation of liquid to vapor. So it's the same thing. You transform liquid to vapor is to spread out further the particles from one another. So the greater the dispersion between the particles as liquid turns gas is increasing the entropy. So comparing the entropy between a liquid and its vapor state, the entropy in its vapor state or gaseous state is greater because of the greater spaces between particles. There are more spaces for that results to increase in their chances for movements. So increasing the chances for movements, increasing the disorder is increasing the entropy of the system. So comparing the entropy between liquid and vapor, it is always greater. The dispersion is always greater in vapor or gaseous than in. What about the effect of increasing temperature in the system? Increasing temperature, as we all know, results to increase in kinetic energy. So the greater the degree of movement among particles in a system results to increase in microstates. So greater number of microstates means greater possible ways to disperse the energy in the system. So increase in energy is always resulting to increase in disorder, hence increase in the entropy of the system. So if we are to compare the entropy of a colder system and a hotter system, it's always in the hotter system that we expect a higher degree of disorder and therefore higher value for entropy. Lower amount of entropy in the colder system. So as you increase the temperature of a system, you are increasing the entropy of the system. In terms of mixture or combination of pure solvent and pure solute, we expect that the entropy or the order of particles in the pure solvent and pure solute are better. So they have better arrangement of particles when they are in their pure states. When they are mixed together to form the solution, they are more dispersed with one another. So notice in the illustration on the right, we have the solute particles that are dispersed with or in the solvent particles. So they are separated in the solution as well as the solvent particles. So the degree of disorder for both solute and solvent is greater when they are in a solution. Plus, the dissociation of, if it's solid, for example, solid salt, the dissociation of or the ionization of sodium chloride to sodium ion and chloride ion also increases the entropy of the system. So comparing the pure solute and solvent with the solution as they combine together is changing or increasing the entropy of the system of the two. So a solution always exhibits higher or obtaining higher entropy than the pure solute or solvent. In the previous video, we studied about the standard enthalpy. This is the energy lost or absorbed by the formation of a molecule or a compound from their constituent elements. For example, the formation of carbon dioxide. The formation of carbon dioxide from the constituent elements carbon and oxygen is accompanied by a release of energy. There are molecules and substances that are formed with release of energy. There are those that are formed with absorption of energy. They are constant, they are predetermined, and list of them are usually seen on the appendix section of the chemistry books. So in this lesson, we have standard entropy. So again, entropy is the measure of disorder of a system or in a system. Standard entropy is the absolute entropy of a substance at standard conditions 1 atm and 25 degrees Celsius. We have here some standard entropy values for some substances at 25 degrees Celsius. Let's compare the standard entropy values of liquid water and gaseous water. Earlier, we have established that the liquid form of a substance has higher degree of disorder and therefore higher entropy. Same with between gas and liquid state of the substance. The gaseous state has higher degree of disorder and therefore higher entropy than its liquid state. So if you have here water in two different states, liquid and gas, we expect the degree of dispersion in gaseous to be greater and therefore the entropy value is also greater than the liquid state, which is only 69.9. The unit of standard entropy is given as joule per Kelvin dot mole. Between liquid and gaseous states of bromine. So we have gaseous bromine with higher entropy because of greater degree of dispersion by particles. Same with iodine crystals or solid and iodine gas. So 260.6 for gaseous, 116.7 for solid. For diamond and graphite, the atoms in diamond are more orderly than those in graphite. Therefore, the disorder of atoms of carbon is higher in graphite than in diamond. More orderly in diamond, less orderly or more disordered in graphite, and therefore higher entropy value for graphite. Between methane and ethane, both of which are organic, but notice the molar mass. Aside from the higher molar mass of ethane, because of a higher number of atoms, the structures also are different for the two. More atoms of ethane result to more complex structure. So in terms of structure, the more complex molecule or structure for a substance results to higher entropy value. For helium and neon, we have same substances under same nature, both of which are inert gases, noble gases. But between the two, neon has higher molar mass. So the one with higher molar mass tends to have higher entropy values. Let's predict from among the following which will have greater or less than zero change in entropy. Change in entropy may be determined by subtracting the entropy of the final state and the entropy in the initial state. So let's have number one, freezing ethanol. So after ethanol has frozen, it becomes solid. So the initial state is liquid, the final state is solid. So comparing the entropy of the final state and the initial state of the substance alcohol, which has higher entropy. The final state is solid, the initial state is liquid. So liquid being the initial state has higher entropy. But subtracting the entropies for the two states to get the change in entropy, we subtract final has lower entropy minus the initial of higher entropy. You will have change in entropy that is less than zero or negative entropy. Because the final state, solid, has lower entropy than the initial state, which is liquid. Let's have number two, evaporating a liquid bromine at room temperature. So evaporation is the process. The initial state is liquid, the final state is gas. So the final state has higher entropy than the initial state, and therefore subtracting the two, you will have a change in entropy that is greater than zero or positive entropy. Number three, dissolving glucose in water. So earlier, we had dissolution of solid, for example, solute in liquid, for example, water. So dissolution results to increase in disorder between the particles of both the solute and the solvent. So in this case, we have the glucose as the solute and water as the solvent. As glucose dissolves in water, it spreads out in water. Water also will be spread out because glucose particles will occupy the spaces that are originally occupied by water in the solution. So the disorder as the two mixes together is increased. So the final state has higher entropy than the initial states, which are the pure glucose and pure water. So the change in entropy is expected to be higher because solution is the final, the pure is the initial. Getting the difference, you will get a positive change in entropy value. Number four, cooling nitrogen from 80 to 20. So the initial state is 80. It is higher than the final 20. Final 20 minus initial 80, you will get a negative value of temperature. So that negative value of temperature means increase in, cooling nitrogen from 80 to 20. That will mean from hotter, nitrogen becomes colder. So the initial with higher temperature has higher degree of disorder than the final with lower temperature, with lower entropy. And therefore, the change in entropy is expected to be less than zero. From higher to lower, final is lower than the initial. And for number five, subliming dry ice. So sublimation is the process of turning solid to gas without passing the liquid. So if the final state is gas, the initial is solid, then it is higher minus lower, you will get a positive value for change in entropy. And therefore, the change in entropy is greater than 0 or positive if we are to determine it more uh, in details or quantitative. Let's now go to the second law of thermodynamics. This law describes the entropy of the universe. It states that the entropy in the universe increases in a spontaneous process and remains unchanged in an equilibrium process. In equation, we have the change in enthalpy in the universe to be greater than 0, calculated as the sum of the entropy of the system, change in entropy of the system, and the change in entropy of the surroundings. So if the change in entropy is positive, then we consider the system or the process to be spontaneous. For an equilibrium process, the change in entropy in the system is numerically the same as the change in entropy of the surrounding, but in opposite sign. And the sum of the two is equal to 0. If you have enthalpy of standard enthalpy of reaction, which if you recall, the difference between the enthalpies of formation of the products minus the enthalpies of formation of the reactants multiplied by their stoichiometric coefficients, we also have standard entropy of reaction under the second law of thermodynamics. This is denoted by delta S superscript 0 subscript reaction. This is the difference between the standard entropies between the products and the reactants. So if we have a particular chemical reaction, that is what we consider the system. So to determine the entropy of standard entropy of that system or of that particularly of that reaction, we get the difference between the standard entropies between the products and the reactants. In equation, the entropy of the reaction is calculated as the difference between the standard entropies of the products and the standard entropies of the reactants multiplied by their stoichiometric coefficients. So if we have a hypothetical equation A plus B equals forming C and D with their stoichiometric coefficients, small letters A, B, C, D, we can express the standard entropy of the reaction as follows. Open and close brackets, standard entropies of the products C and D added but multiplied first by their respective coefficients minus the sum of the standard entropies of the reactants multiplied also by their coefficients. Our reactants here are A and B. Our products are C and D. And then you multiply first by their coefficients before you subtract. In the appendix sections of most books, you will see a summary of the standard enthalpies of formations of some substances or most common substances. We also have, that is in the first column. We also have in the last column the standard entropies of the substances. For example, let's have carbon dioxide. Gaseous carbon dioxide has standard enthalpy of formation negative 393.5. Standard enthalpy of formation is the energy given off or absorbed as the substance forms from its constituent elements. For example, carbon dioxide is formed from carbon and oxygen. The formation of carbon dioxide from carbon and oxygen is accompanied by release of 393.5 kilojoule per mole. In the fourth column, you will see the standard entropy of carbon dioxide, which is positive 213.16 per mole. So 1 mole of carbon dioxide has standard entropy of 213.6 joule per Kelvin. Yeah, you will see the standard enthalpy formations of and entropies of some substances or common substances in many books of inorganic chemistry. So we have for nitrogen, the standard enthalpy of formation is 0. The standard entropy is 191.5 because it is in the gaseous state. You expect higher degree of disorder and therefore higher value for NP. We also have the standard enthalpies of formation for liquid water and gaseous water. So notice the entropy. Let's have the last column. Entropy of gaseous water is higher than the entropy of liquid water because again, gaseous state of water has higher degree of disorder, hence higher value for entropy. Let's try to calculate standard entropy change for a reaction. Let's have this reaction. 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia, also gas in the gaseous state. In here, you will see the list of standard entropies of the substances involved in the reaction. We have 3 substances: nitrogen, hydrogen, and ammonia. Their standard entropies taken from the appendix of the book are hydrogen 131, nitrogen 192, and ammonia 193. You will be using these constants in computing for the change in entropy for the reaction. So using the hypothetical equation A plus B equals C plus D with their coefficients, we write the change in entropy, change in standard entropy for this reaction as open and close brackets 2 times the entropy, standard entropy of the product, which is ammonia, minus the sum of the standard entropies of the 2 reactants, nitrogen and hydrogen, multiplied by their coefficients. Okay, so to solve, 2 is the stoichiometric coefficient of our product ammonia. 193 joule per Kelvin dot mole is its standard entropy taken from the table, minus the sum of the standard entropies of the reactants nitrogen and hydrogen multiplied by their coefficients. Between the two, only hydrogen has coefficient 3. So you will first multiply the standard entropy of hydrogen, which is 131 from our table, by 3 before you add the value by or to that to the entropy of nitrogen, which is amounting to 192. You will get the answer. So 2, for the product, we have 2 times 193 joule per Kelvin dot mole minus the sum of the two, 192 joule, 192 plus the product between 3 and 131. You will get the answer negative, a net entropy change of 199 joule per Kelvin dot mole. So the standard entropy change for this reaction is negative 199 joule per Kelvin dot. And let's have another example. Calculate the standard entropy change for the following reaction. Let's have the reaction. 1 mole of molecular hydrogen reacts with 1 mole of molecular chlorine to form 2 moles of hydrogen chloride gas. So on the right, you will see their standard entropies of our substances in the reaction: hydrogen, chlorine, and hydrogen chloride. So referring to the general equation, we shall have the following equation for the standard entropy change for the reaction. We have 2 times the standard entropy of our product, hydrogen chloride, minus the sum of the entropies of our reactants, hydrogen and chlorine, multiplied by their coefficients. Among the 3 substances in the reaction, only our product has a coefficient 2. So you will have to multiply first its standard entropy by 2 before you will subtract by the sum of the 2 entropies, which is of our reactants. So we have the substitution, 2 times standard entropy of the product 187 joule per Kelvin dot mole minus the sum of the two standard entropies of the reactants. We have 131 plus 223. You will get a summation of 20 joule per Kelvin dot mole. So this is the standard entropy change for the reaction. Notice we have different values. Earlier in the first example, we obtained a negative standard entropy change for the reaction. This time, in this second example, we obtained a positive entropy change for the reaction. Going back to the second law of thermodynamics, which states again that for a spontaneous process, the change in entropy must always be positive. In equation, we have the change in the entropy in the universe must be positive, which is calculated also as the sum of the entropy change in the system and entropy change in the surroundings. Let's consider these situations. You will see in letter A that the system is giving off heat to the surroundings. That heat given off by the system to the surrounding results to increase in entropy in the surroundings, because as we have emphasized in the previous slides, that heat causes increase in entropy because of the increase in microstates. The higher the temperature, the higher the kinetic energy, the higher degree of movements for the particles. On the other hand, in letter B, you will see that heat is being absorbed by the system from the surrounding. That heat absorbed by the system from the surrounding results to increase in entropy in the system. So for every heat given off by the system to the surrounding, that results to increase in the entropy in the surroundings. Or for every amount of heat absorbed by the system from the surrounding, that is also resulting to increase in entropy in the system. So if you are to compare or to have the two compared, they are proportional. For every increase in the entropy in the surrounding, that is accompanied or that is caused, that is due to energy lost by a system. So energy in letter A from the system is given off to the surrounding, which causes increase in entropy in the surroundings. So energy lost by the system is denoted by negative. Increase in entropy is denoted by positive. So having them in an equation, because in the first two examples, when we did our calculations in the two previous slides, we computed for the change in entropy of systems. What we considered systems are the chemical reactions. So in here, we will have the equation for the entropy change in the surroundings, which considers the change in enthalpy or negative enthalpy of the system divided by the temperature of the system. Let's have this simple reaction again that we used earlier. Is the reaction spontaneous at 25 degrees Celsius? So you are given here the enthalpy of the reaction, 92.3 kilojoule per mole. What does it mean again? The reaction between the two gases that results to formation of ammonia is accompanied by release of 92.3 kilojoule per mole. So in the earlier example, we computed the change in entropy of the reaction, and we had negative 199 joule per Kelvin dot mole. Using the equation that we have obtained in the previous slide, enthalpy of the change in entropy of the surrounding is equal to negative change in entropy of the system divided by the temperature of the system. Substituting the values, we have negative is given, is constant. The enthalpy of the reaction is negative 92.6 times negative 92.6. We just need to multiply by 1000 to convert a kilojoule to joule. to proceed with the operation. Per mole over 298 Kelvin is the conversion of 25 degrees Celsius to Kelvin. That's adding 273 to 25 to become 298 Kelvin. Without having to cancel any unit, we proceed. Negative times negative is positive. 92.6 times 1000 is 9,200, 92,600 joule per mole over divided by 2,298 Kelvin. That will give you 311 joule per Kelvin that mole. Using now the equation from the second law of thermodynamics, we have the change in entropy in the universe is the sum of the entropy change of the system and entropy change of the surrounding. And for the reaction to occur, the change in entropy in this universe must be positive. So if that is positive, then we conclude that the reaction at 25 degrees Celsius occurs spontaneously. So we have calculated the entropy change of the system earlier to be 199, negative 199 joule per Kelvin that mole. Add that to our calculated entropy change in the surroundings. That will be 311 joule per Kelvin that mole. Getting the sum, you have 112 joule per Kelvin that mole. So again, since this is positive change in entropy in the universe, then this reaction occurs spontaneously. If you noticed, most of my chemical reactions in my examples are exothermic. Exothermic reactions or processes are those that give off or release energy, because spontaneous processes or reactions are normally associated with exothermicity. Let's have this example. The reaction or the combustion of methane with oxygen to form carbon dioxide and water is a spontaneous process. It is exothermic because the reaction is accompanied by release of 890.4 kilojoule per mole. This is the reason why we are able to cook using our LPG, because of the heat energy released for every mole of the LPG burning with oxygen in the atmosphere. Another example is the formation of water from the acid-base reaction that is accompanied by release of 56.2 kilojoule per mole. So these two are exothermic reactions or processes accompanied by release of energy and are both spontaneous in one direction. But there are exothermic reactions or processes also that are spontaneous even without the release or giving off of energy. For example, the transformation, the process of transforming solid to liquid. As you know, ice, as it absorbs heat energy from the surrounding, it spontaneously melts. Solid water is absorbing energy and is melting spontaneously. The process is spontaneous, but the energy is absorbed by the system. Another is the ionization or dispersion of the ions of ammonium nitrate when dissolved in water. So this ionization of ammonium nitrate in water is accompanied by absorption of 25 kilojoule per mole. So these two are just two examples of endothermic processes that are spontaneous, but they are absorbing energy. This another example of endothermic reaction is non-spontaneous at room temperature. That is, for example, 25 degrees Celsius. This is non-spontaneous. But as temperature is increased, it becomes spontaneous, absorbing 90.7 kilojoule per mole. So what does it mean? Ethnothermicity nor endothermicity of processes or reactions do not guarantee spontaneity of reaction. So how do we determine if a reaction is indeed spontaneous or non-spontaneous in one direction or in the opposite direction? That's why we need to consider another thermodynamic quantity, which is called the Gibbs free energy, or simply free energy. This is the energy available to do work and incorporates both the enthalpy and entropy in a single value. In equation, free energy is the difference between the enthalpy of a system minus the product of the temperature and entropy of the system, or change in free energy is equal to the difference between the change in enthalpy and the product of temperature and change in entropy of the system. To determine whether a reaction is spontaneous in one direction or in the forward direction, the change in free energy must be less than zero or any negative value. When the change in entropy is positive or any number greater than zero, the reaction is non-spontaneous, but it is spontaneous in the opposite direction. But if the system is at equilibrium, there is no net change, meaning there is no difference in the enthalpy, in the free energy, in the forward direction, and in the opposite direction. They are equal in magnitude. Let's now consider the standard free energy of reaction, denoted by delta G superscript 0 subscript reaction. This is the free energy change for a reaction when it occurs under standard state conditions. That is, when the reactants are in their standard states and are converted to products also in their standard states. In equation, we have the standard free energy of reaction equals the difference between the free energy of formation of the products and the free energy of the reactants multiplied by their stoichiometric coefficients. So if we have this hypothetical equation A plus B forming C and D with their stoichiometric coefficients, we shall have the general equation for the standard free energy of the reaction, which is the open and close brackets, the sum of the free energies of the products minus the sum of the free energies of the reactants multiplied by their stoichiometric coefficients. Let's have this example. What is this standard free energy change for the combustion of graphite? Graphite is carbon. When that is made to react with oxygen gas, carbon dioxide forms. We have 1 mole of carbon reacting with 1 mole of oxygen gas to produce 1 mole of carbon dioxide gas. For the standard free energy change for this combustion reaction, we have the free energy of our product, which is carbon dioxide, minus the sum of the free energy of our reactants, which are graphite and oxygen. Substituting from the table of the constants, we will have the values. In the second column, rather in the third column, you will see the free energy of carbon dioxide, which is negative 393.4 kilojoule per mole, minus the sum of the free energy of our reactants, graphite and oxygen, which happen to be both 0. So that will give us the summation, negative 393.4 kilojoule per mole. Recalling Gibbs free energy conditions for spontaneity of reaction, when the free energy of the reaction is less than 0, that is, any negative value, the result is that the reaction is spontaneous in the forward direction. If it's greater than 0 or any positive value for free energy, then the reaction is non-spontaneous, but is spontaneous in the opposite direction. So if we are to classify this whether spontaneous or non-spontaneous, since this is negative, less than 0, then this reaction is spontaneous in forward direction. Let's have another example. Quicklime, prepared by decomposing limestone at a high temperature, is an extremely valuable inorganic substance that is used in steel making, calcium metal production, paper industry, water treatment, and pollution control. This is the reaction accompanied in the formation of the quicklime. We have calcium carbonate, the limestone, decomposing to calcium oxide and carbon dioxide. Let's first compute for the enthalpy of the reaction. So as we have discussed in the previous video and in the previous slides, the enthalpy of the reaction is calculated by getting the difference between the enthalpies of formation of the products and the enthalpies of formation of the reactants. In this reaction, we only have one reactant, which is calcium carbonate, and we have two products, calcium oxide and carbon dioxide. So from the table of constants, we get the enthalpy of formation of calcium oxide, one of our two products, negative 635.6. You add that with the enthalpy of formation of carbon dioxide, our other product, negative 393.5. The sum of the two reactants, enthalpies of formation, will be combined by subtraction with the enthalpy of formation of the reactant, which is, we only have one, calcium carbonate. Its enthalpy of formation is negative 1206.9. Getting the sum of the enthalpies of formation of our products and having that subtracted with our enthalpy of formation of the reactant, we will have the summation 177.8 kilojoule per mole, which is positive. For the change in entropy of the reaction, we also get the difference between the standard enthalpies of the products minus the standard entropy of the reactant. Again, we only have one reactant, which is calcium carbonate. We have two products, calcium oxide and carbon dioxide. So from the table of constants, you will get again their standard entropies. So the standard entropy of our calcium oxide is 39.8. Our carbon dioxide is 213.6. Get the sum of the two products. Have that subtracted with the standard entropy of our reactant, calcium carbonate, which is 92.9. Getting the difference, you will get 160.5 joule per Kelvin dot mole. Using now the equation for the change in free energy of the reaction, we have the equation change in enthalpy minus temperature of the system and the change in entropy in the system. Substituting now the calculated we have the calculated change in enthalpy, 177.8 kilojoule per mole, minus 298 Kelvin is 25 degrees Celsius plus 273 to convert 25 degrees Celsius room temperature to Kelvin. So that will give you 298 Kelvin. The change in entropy in the system is 160.5. But we need to convert joule to kilojoule. So we use the conversion factor 1 kilojoule over 1000 kilojoule. Sorry, 1000 joule. Cancel the similar units joule as well as Kelvin. We will get the answer 130.0 kilojoule per mole. So this is now our change in free energy of the reaction. Notice that unlike in our first example, we have obtained negative free energy for the reaction. So that gives us the idea that the reaction is spontaneous. But having the reaction gives free energy of the reaction positive, we cannot tell that the reaction is spontaneous. But since we need to obtain calcium oxide from this reaction for the purposes of, as we said in the problem, extremely valuable inorganic substance that is used in many purposes, we have to make the most out of the reaction. So what do? We control the system. We set a standard condition for the system. And to do that, let's assume, so this 130 kilojoule per mole is at room temperature that we have set initially, 25 degrees Celsius. Let's set, so this is 130. Let's assume that the change in free energy is 0. So if this is 0, using the original equation, free energy of the reaction, 0, equals the difference between the change in enthalpy of the reaction and temperature times the change in entropy of the reaction or of the system. We substitute, or we derive first the temperature of the system. So to derive that is to transpose negative T delta S to the opposite side, to the other side of the equation, and then transposing again delta S to the right side of the equation. So we shall have delta H, or change in enthalpy of the system, over change in entropy of the system. Substituting the calculated values, we have 177.8 kilojoule per mole. Convert that to joule. So use the equation or the conversion factor 1000 joule per 1 kilojoule divided by the calculated change in entropy, which is 160.5 joule per Kelvin dot mole. Canceling the necessary units to cancel, we have Kelvin left. 1108 Kelvin is the temperature of the system if the change in free energy is 0. So to make the free energy less than 0, then we increase the temperature. Instead of 1108 Kelvin, we increase that, let's say, by 5 Kelvin. Because this is resulting to 0. This temperature, 1108 Kelvin, is giving us a 0 free energy, and therefore does not guarantee spontaneity of the reaction. So to obtain a negative value of free energy, we use temperature that is higher than this temperature. So let's say we add 5 Kelvin. Let's make this 1113 Kelvin. Using the original equation for change in free energy, we substitute 177.8 as change in enthalpy and 1113, the condition we set for the reaction, and then the calculated change in entropy of the reaction, 160.5 kilojoule. Convert that again to joule, convert that again to kilojoule, canceling the necessary units. We will have negative 0.8 kilojoule per mole. We now have a negative value of change in free energy. And that will make our reaction spontaneous in the forward reaction. So if this is made spontaneous in the forward reaction, then the manufacturing companies can maximize the formation of calcium oxide from this reaction by setting a temperature that is higher than 1108 Kelvin. So that is the application of the second law of thermodynamics. So that will be all for this lesson. Thank you for watching and listening. Until next time.